Okay, we now move on to chapter 2, which is multivariable calculus. So when you look at multivariable calculus, all it means is that this is the calculus of a function which is dependent on two or more variables. Okay, so what is an example of a naturally occurring function in the physical system that we have learned so far, which is of two or more variables? So one example could be, right, so one example could be the wave function, right. Wave function in general is a function of position and time. If you look at a wave function in 3 dimensions, then it is a function of the 3-dimensional coordinates x, y and z and time. So now this becomes a 4-dimensional or a function which is dependent on 4 variables, right? 3 variables of coordinates and 1 variable which represents time. Then there is another quantity that we have already studied in our second year, which is thermodynamic quantities, right? So this we have already looked at. So for example, enthalpy, which can be a function of temperature and pressure, or right, so this is enthalpy. I hope you guys remember and have not forgotten thermodynamics. Then this is entropy, which is again a function of temperature and pressure, right? So in all of this, we actually used multivariable calculus when we carried out the partial differentials of these functions. Okay. So for example, what I mean by differential. So if z is a function of x and y, right, then the total differential dz is now the total differential, right. So dz will be, this we have already seen in thermodynamics, but I'm just trying to recapitulate so all of us can be on the same page. So dz is equal to dou f by dou x at constant y into dx plus dou f by dou y at constant x into dy, right. So this is our total differential. So this is equal to dx. So what does this mean, right? So when we take, so let's go back to a one variable system. Let's say if z is equal to f of x, okay, and then if we were to take dz, we would have dou f by dou x, right, into dx, okay. So basically this would give us dz by dx is nothing but df by dx, because there is only one function here, right, or it is dependent on only one variable, which is x. We don't have to write it in terms of partial derivatives. We can just write it as dz by dx is equal to df by dx, okay. So this is how we write the differential for a system which is dependent on only one variable. So what does this z mean, right? What does this dz by dx actually mean? Okay, so this means, let's go here. So if we on an axis we have z, which is equal to f of x, and we have x, right, and let's say we have a curve. Okay, so now dz by dx actually represents the slope. Okay, and the way to calculate the slope is to consider 2 points on the curve, right. So these are the 2 points, and now this is your on the z-axis. These are the 2 points, right. So this point, let's call this point A and let's call this point B. So point A is x1, z1, and point B is x2, z2. So your dz by dx is nothing but, and your distance here is delta x, okay. So your dz by dx is nothing but basically z2 minus z1 by delta x. So this is what your dz by dx is, okay, which is nothing but your delta z by delta x in the limit that delta x tends to 0. Okay, so this is what it means. Alright. Now of course, if we have a two variable function, okay, so for a two variable function, your z is of course a function of two variables. So your dz is nothing but, we have already seen, dou f by dou x at constant y into dx plus dou f by dou y at constant x into dy. Alright. Okay. So this is your dz, and what this means is that now because z is a function of two variables, or here in this case if we assume that x and y are the directions or the coordinates in the coordinate system, then the slope of z will also have two directions, one in the x direction and one in the y direction, and that is what is represented by the total differential. Okay, so basically the differential represents the value of slope in the two directions. Okay, this is what we mean by the differential. If you have three variables, then it will represent the value of the slope in the three directions, okay, or in the three coordinates. Alright, so okay, so we can see this. So of course, if we represent it in the polar coordinates, we will look at polar coordinates in detail later, but let's say you have a vector r in the xy plane. Okay, so this is your vector r. Alright, so if this is your vector r and it makes an angle theta with respect to the x direction, then we can write x is equal to r cos theta. So let's say this is capital X, and so let's say this is your x dash and this is your, this is x, and this is y. So x is basically r cos theta and y is equal to r sin theta. Alright, so now if you want to take a differential dx, the total differential dx, x is a function of, here it is a function of r and theta. So you can take the differential for dx in the two directions. So what you will get is dx is equal to dou f by dou r at constant theta into dr plus dou f by dou theta at constant r into d theta. Right? So what is f? F is nothing but r cos theta. And so dou f by dou r at constant theta, right? So we are assuming that theta is a constant for this term we will assume that theta is constant, and for the other term we will assume that r is a constant value. So if for this term we have theta is constant, then we only differentiate with respect to r. So differential of r is nothing but 1. So you have 1 into cos theta. So this is nothing but cos theta. And similarly you have differential of theta at constant r. So r is assumed to be constant, and now we are differentiating with respect to theta. Right? So this will give us minus r sin theta. Okay. So finally we can just plug this there. So dx will be cos theta into dr, and this other value would be minus r sin theta d theta. So this is your total differential for dx. Similarly, you can do for dy, right? So I'll just write the final answer, you can verify it. So dy is nothing but, so dou f by dou r at constant theta, so you would get sin theta into dr plus r cos theta d theta. So this is what you would get for dy. Alright. Now just to recap, let's revise the differential formulas. Formulas for differentiation. Okay. So in order to revise the formulas for differentiation, let's just look at it quickly. So if you do d by dx of x power n, right, where n is a constant, okay, so what you will get is n into x power n minus 1. Alright. If you do a differentiation of d by dx of sin x, you will get cos x. If you do d by dx of cos x, you will get minus sin x. Okay, these are the formulas. I think these are important formulas, so you should know them. Then d by dx of ln x will give you 1 by x. Okay. And then d by dx of e power x will give you e power x. Okay. What if you have a constant? So d by dx of let's say 2 cos x. Then 2 is a constant, so it won't change. So what you are doing is you just keep it outside. So you do 2 into d by dx of cos x. So you'll get, now you can apply this formula, which is minus 2 sin x. But what if you want to do d by dx of cos 2x, right? So now cos 2x could be some function, right? So what you have to do is, you have to, so this is like y of x. Let's call this y of x. So you are essentially doing d by dx of y of x. So what you will do is, or y of ax or y of 2x, okay, let's call this y of 2x, right, because 2x is the variable and the function is cos. So if this is your function d by dx of y 2x, then what you have to do is, you have to assume, first you have to do a differential of d by dx of y, and then you have to differentiate the function inside. So the function inside is d by dx of 2x. So this is what you have to do. So if you just assume that y is a cos function, then the differential of the cos function will be minus sine, right? So this will just give you minus sine 2x. So this will just give you minus sine 2x, and then d by dx of 2x would just give you into 2, that's it. So finally you would get minus 2 sine 2x. Okay, so this would be your function. So in general, if you want to do f dash or f of ax, right, then you would do d by dx of f, the original function, into d by dx of ax. This is what you would have to do. Okay. So this is I think known as the product rule. Now suppose you have a function right, which is sine x into cos x. Okay, in this case what you have to do, this is also a function of x, let's call this f1 of x, and this is also a function of x, let's call this f2 of x. So this is a product of two functions of x. Okay, so in that case what you do is, you first do not change this, right? So basically you do f2 into df1 by dx plus f1 into df2 by dx. So here you will have f2, which is cos x into cos x, because d sin x by x is, d by dx of sin x is cos x, plus sin x into minus sin x. So this is your answer. So you would get cos square x minus sin square x. So this is your differentiation. Okay, so in general you can get d by dx of f1 of x into f2 of x is basically nothing but f2 of x into df1 by dx plus f1 of x into df2 of x by dx. Okay, so this is what you will get. Alright, so I'll give you some small problems for those of you who have difficulty or who think that differentiation is hard. I want you to practice with these problems. So first, this is differentiate the following with respect to x. So 1, you would have e power ax, 2 x power 2n, 3 cos 5x, 4 cos 3x by sin x, 5 log of 2x. Okay, so I think that will do. So these are the 5 problems. You can try them out. If you are able to do these problems, you will not have that much difficulty in following multivariable calculus. Alright. Now let's go to some expansions. Okay, so there are some functions, for example sin x, cos x, e power x. So these are functions which in certain limits can be written in a series form. Alright. So the general form to write something in a series, okay. So let's say there is a function f of x and we want to represent this in a series. Okay. So what we will do is f of x is equal to, because this is there is only x, so we will assume that this is expansion about 0. Okay, so we will write f of 0 plus x into f dash of x at, so only for this term we will put at x equal to 0, plus x square by 2 factorial for f double dash of x at x equal to 0, plus x cube by 6 factorial, sorry, x cube by 3 factorial, which will be 6, f triple dash of x at x equal to 0, plus so on. So this function, so this kind of series expansion about x equal to 0 is known as Maclaurin series. Okay, it's called a Maclaurin series or a Maclaurin series expansion. Okay, so here let's look at an example. So let's say, so now the one thing that you have to remember is this series expansion cannot be done for every function of x. Okay, so if you have f of x is x square, if you do this series expansion, you will keep getting x plus x square plus x cube, right? So this series will never converge. In basically this series is going up to infinity, right? But if you go on up to like that, you will get x power 100, x power 1000 at some case, and that number will keep on. So if x is 2, you will get 2 power 1000. So the number is going on increasing, right? So initially the function was x square, and that is definitely not equal to x power 1000 if x is greater than 1. Okay, so this series always needs to converge. So the condition for convergence is that always only those functions are expanded into a series form which converge. So the way that the series will converge is you take a function, for example e power x, right? Now if x is equal to minus 5, also if x is equal to 0.1, right, then you will see that the series is actually converging, because as you go to the multiples of x, right, ultimately you will get 0.1 power 1000, right, which is nothing but right, 10 power minus 1000 actually. So if that is 10 power minus 1000, that is a very small number. So basically the series is converging when when you are going on increasing up to infinity. So the criterion has to be followed. So let's look at an example. So let us expand sine x. Okay, so what is sine x? So this expansion can be done into series. So expand sine x into series for x less than 1. So only when x is much less than 1 can you do this expansion. So how will you do it? So f of x is sine x. So f dash of x is, so f of x is sine x. So f of 0 is sine 0, which is 0. F dash of x is d by dx of sine x, which is nothing but cos x. So f dash of 0 will give you cos 0, which is nothing but 1. Okay. Now f double dash of x is d2 by dx square of sine x, right, which is nothing but d by dx of f dash of x, which is d by dx of cos x. So we will get minus sine x, right? So f double dash of 0 is that you now substitute 0 for x. So you will get minus sine 0, which is 0. Okay, so you can keep doing it that way. So finally you will get sine x is nothing but f of 0 plus x into f dash of 0 plus x square by 2 factorial into f double dash of 0 plus x cube by 3 factorial into f triple dash of 0 plus so on. So finally you will get this term as 0, right? This term is 0. So basically all the even terms are going to be 0. So you will get, and all the odd terms will turn out to be 1. 1 or minus 1. So finally you will get right. So you are going to get x. So f dash of 0, right? That was 1. So x minus x cube by 3 factorial plus x power 5 by 5 factorial minus so on. So this is your sine x. Okay. So let's have a homework. So your homework is expand e power x into a series for x much less than 1. Okay. So this is your expansion. This is your homework. There is another series expansion called Taylor series expansion, and this is done for expansion about a particular value. Okay, about a particular number or value, let's say a. So if you want to expand f of x minus a, right? So f of x minus a is your function, and you want to expand this into series. So basically what you will do is f of x minus a is nothing but f of a plus x into f dash of a plus x square into f double dash of a plus x square by 2 factorial, right? So plus x cube by so that this will be x minus a into f dash of a plus x minus a whole square by 2 factorial into f double dash of a plus x minus a whole cube by 3 factorial to f triple dash of a, and so on. Okay. Alright. So this is your Taylor series expansion. Alright. So if you want to now expand a product of two functions, okay. So let's say you want to expand sine x into cos y. Expand this into series. Now this expansion is a Maclaurin series expansion because this is expansion about 0, right? So you will do the same way, and for sine x you will get x minus x cube by 3 factorial plus x power 5 by 5 factorial minus so on. And for cos x and for cos y you will get 1 minus y square by 2 factorial plus y power 4 by 4 factorial and so on. Okay, so sin x cos y is nothing but the product of this. So you will have x minus x cube by 3 factorial plus so on, 1 minus y square by 2 factorial and so on. So this is the series expansion. So you can expand it to a few terms. So you will get x cube by 3 factorial minus xy square by 2 factorial and so on. Okay, so this is what you will get. So your homework is find the series expansion for e power x plus 2y.